Hey everyone, I'm Jose from OpenZeppelin, and today I'll be walking through the Sui AMM. It is a reference built for a proprietary AMM on Sui, but when you hear the word AMM, you might picture a liquidity pool that traders swap against. This one's a different model, so let's just clarify that first. It's an on-chain program that an individual market maker runs to post buy and sell orders on an exchange's order book. It follows a price oracle to keep those quotes fair and earns the gap between the two when both sides gets filled. The gap is called the spread, by the way. It runs entirely on-chain as a Move package. Its prices comes from the PIT network. Its orders goes to DeepBook, which is Sui's native order book. And the interesting part is that anyone can keep its quotes fresh, not just the owner. The Move type system is what makes that safe. So in this video, I'll try to provide a high-level walkthrough. If you are newer to Sui or Move, I'll again try to explain things as we go. But of course, our documentation and the repository itself are all linked in the description if you want to go deeper. And with that, let's get into it. Architecturally, we have a shape you would expect on Sui. One published Move package called Prop AMM with 5 Move modules plus DeepBook v3 and PIT as external dependencies. The TypeScript layer lives in packages domain, and it builds every PTB, the UI, and the bot to submit. And the Next.js dApp sits on top, but every UI action and every background bot funnels through the same domain level PTB builder. So like there's exactly one place to read if you want to understand what it's chain, and it is exactly here. And before we open the modules, let me give you the user flow mental model. There are basically 3 roles here. The owner is the person who created this market maker. They are the only one who can deposit funds, change configuration, or pause it. They hold a capability object in their wallet that gates all of these functions. And then there is anyone. And I really do mean anyone. The owner included, but also keepers or other bots. Anyone can call the refresh function to update the 4 orders sitting on the book. About those 4 orders, I will mention more about them, and actually we will see them in demo live. So that was the permissionless part that anyone can call. And finally, of course, anyone trading on the DeepBook can fill those orders just like any other limit order. The interesting safety story is making sure that even with refresh being open to anyone, no bad order can ever end up resting on the book. And in this video, I'll try to show what we are trying to prevent to happen with our assertions, with our security checks, to see how we prevent bad things to happen. Now, about these 5 modules. Market handles the pool identity and PIT fits. Config holds the AMM parameters. Executor is the central piece basically. It owns the shared object, the embedded balance manager, and the quote refresh itself. And then info handles accounting, and events is the event surface. With that in mind, let's get into code. First, let's take a quick look at the package manifest, which is Move TAML. We've got 2 external dependencies here, DeepBook v3 from Mr. Labs pinned to a specific commit, the PIT from PIT network repo. For testnet and mainnet, we point at the live DeepBook publishes at the dependency replacements here. For localnet, which is what we'll be using today, there is a local PIT mock that replaces the real PIT, so we can run end-to-end with more control. With that, we can start looking at the modules themselves. Let's start with market.move. The first function we are going to check is the function new, which is the constructor here. And what I want to point out is what it refuses to build. Firstly, the pool, the DeepBook pool, has to be whitelisted. And that's not a stylistic choice, because non-whitelisted pools charge a maker fee in the input assets whenever you pay the fee in something other than Deep token, which is DeepBook's protocol token, by the way. And this AMM allocates 100% of each side's balance to its 4 orders. So actually there is no room left over for fees. So on a non-whitelisted pool, the second order on each side will just abort, and we just reject those right at construction. Second check is both PIT feed IDs have to be exactly 32 bytes. And of course, they have to be different from each other. If you use the same feed on the both sides, the price will always come out as 1, and that doesn't make a proper pool, I would say. Also, the asset decimals are bounded by 19, so the on-chain power of 10 math we are using never overflows. And what's worth noting here is that none of these are runtime sender checks, the kind that ask is the caller admin or not. These are argument checks at the function signature, so a buggy PTB literally can't build past them. And another function we can check down here is DeepBook price. This is where PIT's base over USD and quote over USD prices gets combined into a DeepBook fixed point price plus a combined confidence ratio. Each side's confidence ratio also checked individually against the maximum confidence ratio that is allowed. And the function has 2 branches for decimal adjustment, one going up and one going down, to keep the intermediate U128 from overflowing across token pair decimals. And with that, we can close the market.move. Next file is config.move. We will again start with the function new. This is where every AMM parameters gets rank checked. Each BPS field has its bounds asserted basically. For example, the base spread BPS has to be between 0 and 100%. So both 0 and 100% are exclusive. Another interesting one is a cross-validation between two fields. The order expiration time can't exceed the max pit price stage times 1,000. And the reason for that is that an order living longer than Oracle's freshness window could end up quotable against a stale read that the executor will normally reject. So the type system just makes that configuration impossible to construct, and we prevent it again in this place. A bit further down, we should see that is stale tolerant function. This is our defense again FIFO, first in, first out priority grief. Quick context on what that means. DeepBook fills orders at the same price level in the order they are placed. So the first one in will be the first one out. So if we have a great spot in the queue at some price and we cancel our order to repost a new one, we go to the back of the line. And that's the priority we are trying to protect, because anyone can call the permissionless refresh, as I mentioned before. In theory, anyone that called that refresh could pummel us with refreshes on every tiny pit update and force a cancel and replace. That puts us behind the queue every time. So what we do here is compute a worst case ladder drift. That's mid drift plus a confidence drift. And we are trying to weight that by how much of the balance sits in the outer ring. And we skip the refresh when the total drift is below the configured tolerance. And that tolerance itself is bounded by the base spread, as we can see in here. So a skip refresh can never hide a price shift large enough to move an order across the inner placement distance. So if you set the tolerance to 0, the guard just disables, and that's the original behavior that you can opt in or opt out. Another function I will show is right here, reservation mid. This is the inventory skew. When our inventory is unbalanced, we shift the mid toward the side that rebalances the book. So if we have more base than quote, meaning more Sui than USDC in our pool, buyers will see a slightly better bid from us. If we have more quote than base, sellers see a better ask. And again, the shift itself is bounded by the base spread, so the inner order on the rebalancing side never crosses the Oracle mid. We are basically never going to quote worse than the truth on the side we are trying to rebalance towards. And with that config out of the way, let's move to the big one. Now, we are at the executor.move. This is the central module. It's where the shared object lives, where the capability gated functions live, and where the quote refresh logic itself lives. The PIT's price info object and the DeepBook's pool objects aren't owned by this module, by the way. Those are external shared objects. The executor just references during a refresh. But everything else, the executor owns basically. Let's walk through the structs at the top of the file. The first one is admin cap. That's the capability object I mentioned earlier, the one only the owner holds. And notice it carries an executor ID field. That binding is what stops an admin cap from being used against the wrong executor. So every gated function asserts that the cap's executor ID matches the executor's own ID. Then there is the executor itself. It has key and store, and it gets shared once at creation time. It owns the market metadata, the info accounting struct, and the DeepBook balance manager, along with all three of the caps. Those are the trade cap, the deposit cap, and the withdraw cap. So the wallet never holds the balance manager, the executor does. And then there is the refresh ticket, right here, which is interesting, and we'll come back to it in a minute. But first, let's look at how an executor gets created in the first place. We have create function in here. Basically, constructions happens in a single transaction. Create means the balance manager, all three of its caps, deposit, withdraw, and trade. It creates, of course, the executor itself and the admin cap as well. All of them are created atomically, and this create function returns them in a tuple. Then the caller, which is a TypeScript PTB builder over in packages domain, splits them apart. The executor gets shared as a public shared object, as I mentioned, and the admin cap is transferred to the sender directly. The executor also starts paused, by the way. You can see it in this active field here. It starts as false. So you have to explicitly unpause it before it'll accept a refresh. So the separation here is clean. Anyone can hold a reference to the shared executor, but only the original's creator's wallet holds the cap. Okay, now let's look at what this module exists for. That's the refresh function, or refresh functions, let's say. The first one we will check is the permissionless function that I mentioned before. The one any address can call to keep the quotes fresh, and it works every check we already discussed. The pool identity has to match the market, the executor has to be active, both pit price info objects have to carry the configured feed IDs, and then we hit the replay guards. If there are already open orders and neither pit feed has advanced since last time, we just return without doing anything. A stale Oracle refresh would force us to give up our first in first out priority order, as we mentioned before, for no information gain at all. So we prevent that in here. And then we hit the second skip, which is the stale tolerance guide. The same one we just looked at over in config, as you can see in here with is stale tolerant is called from config. So if the nil, mid, and confidence are within the configured tolerance of the last ones, we skip again. Otherwise, we move on and derive the DeepBook price, derive the reservation mid, and post a fresh 4-order ladder. Just below, there is the admin variant, refresh quotes, which is gated by the admin cap. With this one, the caller supplies the mid price and the confidence ratio, and it basically bypasses the pit altogether. That's useful when you want to quote off a centralized exchange feed instead of waiting for pit, or when you want to test the ladder shape against a known price. And the freshness checks doesn't apply here. The cap itself is the gate. Now, let's come back to that refresh ticket I mentioned earlier. This is the pattern I really want you to take away from this walkthrough. So we need to check the update config. Update config replaces the config and resets the cached pit freshness state, which is fine, but it also returns this refresh ticket object. And the refresh ticket has no abilities, as you can see. There is no has something part. It has no drop, no key, no store, nothing. In Move, an object with no abilities is called a hot potato. The compiler refuses any code path that loses it. So the type system will refuse to compile any PTB that doesn't explicitly consume the ticket before the transaction ends. And only ways to consume it is through one of these 4 functions you see right here. The first one cancels the leave ladder. The second requotes using a mid, the caller supplies. The third one requotes from pit. And the fourth one is a no-op consumer that's only valid when the executor is already paused. Every one of those either replaces the orders on the book or remove them entirely. What that means is there is no code path where you can replace the config and leave the previous ladder live. The book can never contain an order priced under a configuration that no longer exists. That's the AMM's headline safety property, and it's enforced by Move's linear types, not by a runtime check we have to remember to write. There is one last thing I want to show you in this module. That's the actual ladder mat, which lives inside refresh quote inner. The base spread is just the mid times the base spread BPS. The outer spread adds the volatility buffer on top of that. That's the volatility multiplier times pit's confidence ratio. And here's a check that's worth pointing out. If the base spread rounds all the way down to 0 at a very small mid, which can happen with integer rounding, we abort entirely instead of placing a degenerate ladder. We just refuse to quote. Then reservation mid applies the inventory skew, and we end up with 4 prices out of it. Now we came to the explanation of what these 4 prices are. A bit further out from the mid price, which is bit outer, a bit closer in, and then the same 2 on the ask side going to the other way. We will see them more in action in demo. For now, let's continue. If our rounding to that grid ends up making the outer order equal to the inner one, this right here, we collapse the outer to 0 quantity, so we don't post a duplicate. It happens at very small spreads, I can say. And finally, down here, we have try-place limit orders. If we go to there, we will see that we have 2 order types we can take: post only and no restriction. If any of the 4 orders would cross the resting book, post only refuses to place that order. So we never end up with an adverse fail from a stale refresh. The alternative is no restriction, where the crossing portion of the order takes whatever's already resting on the other side. That's what traders call a taker fill. And below that, you'll see that any order whose quantity is below minimum size that's allowed in the pool, just gets skipped silently. So a partially funded side doesn't fail the whole refresh. And that wraps the executor.move. Last module we are going to see is events module. We have 7 event types in total: executor created, executor paused, executor unpaused, executor config updated, and the big one is quote updated, which carries the 4 placed orders here. This is what the dApp subscribes to, what any off-chain indexing service would watch, and what the maintenance bot scans through to auto-discover every executor on chain. And with that, we have everything we need to actually go run this thing. But before we do, let me quickly show you the dashboard so you know what you are looking at when the demo starts. This is a dashboard for one market maker. The chart up here shows 2 prices over time. The blue line is the Oracle mid price. That's what Pitt says Sui is worth in USDC. The orange line is the actual mid price of the DeepBook order book, where real trading is happening. And the bands around them are where this market maker has its order posted, the inners and outers. As I showed in the code, we have bid inner, bid outer, ask inner, and ask outer. The inner pair is the tight ring close to the Oracle mid. The outer pair, however, is the wider one, used when the Oracle's confidence interval widens during volatility. We have active order section in here, 2 bids and 2 asks currently resting on the book. It says cancel because it is from my earlier run. I run it just to show it to you. And then we have the event feed below, pulls every change as it happens, including refreshes, deposits, withdrawals, and pauses. And all of this is live. All of it is on-chain, and the UI is just reading the shared executor object directly. Now, let's go and run it, and I'll come back after I run it. What I've done is pre-create 3 market makers from the same wallets, all bound to the same Sui USDC pool. They each start with the exact same balance, which is 1000 Sui and 1500 USDC each. We have Alice in here. Alice is a type maker, 10 basis points of spread, no volatility ring, no inventory scale. So it's the narrowest ladder of the 3, so it's least likely to cross anyone else's order. That makes it the one we expect to actually trade. Then we have Bob. Bob is the opposite. It's wide and volatility aware, a full % of base spread. The outer ring uses a 2x confidence multiplier, and the balance is split 50-50 between inner and the outer. The whole point of this one is to sit far enough from the mid that getting filled at a bad price is basically impossible. But the trade-off is that most of the trading flow just never reaches Bob's order in the first place. And then we have Charlie. Charlie is the risk-tolerant one, 0.5% of base spread, aggressive 90% inventory skill, and the 50% stale tolerance. But the important difference in here is that its post only is turned off. So it's sending its order with no restrictions. That's the flag I pointed out in the code walkthrough, the one controlling whether crossing orders gets refused or taken. So unlike Alice and Bob, when Charlie's refresh attempts would cross orders that are already on the book, Charlie doesn't refuse the crossing portion. It just executes immediately as a taker fill. Charlie accepts the risk of taking adverse liquidity in exchange for staying constantly refreshed. So we have 3 configurations, 1 pool. Let's start the bots and see what each strategy actually does on chain. So we have 2 bots running off the same signer, a dedicated key pair, so the bots aren't fighting my owner wallet over gas coins. The market activity bot walks the mock Sui USDC price by up to 0.5 cent per tick and fires random buys or sells through the DeepBook pool every 2 seconds. The maintenance bot is the auto discovery one. It scans the executor created events, finds all 3 of our executors, and refreshes each one's quotes every 2 seconds. Let's go back to our executors. So this is Alice's dashboard. Tight ladder, 10 basis points around the Oracle mid. Alice is sitting right on the inside of the book, which means every market order from the activity bot is going to lift Alice's asks or hit Alice's bid before it reaches to anyone else. And on top of that, Alice is also catching fills from Charlie because Charlie has post only off. Every time Charlie's refresh would have crossed Alice's resting orders, Charlie takes them as a taker. Oh, we have some action here. So Alice is making the spread on 2 fronts, activity bot flow and Charlie's adverse refreshes. You can see the event feed is dense, the chart is filled in, Alice is doing the most actual trading. And now over here at Bob, the picture is totally different. Yes, we have no orders yet. That's the full percent of base spread, the white ladder of Bob, plus the volatility multiplier on top. So Bob's orders end up sitting far enough from the mid that Bob's refresh attempts almost never cross Alice's resting orders. There are updated quotes though. That doesn't mean Bob's doesn't update its quotes. And the chart fills in steadily in here as well, but Bob's orders are so far out that the activity bot never reaches them. Alice is between Bob and the mid, just soaking up all the flow. And honestly, this is exactly what a white market maker should do. Stay out of the way, except that you'll trade less, but never get caught taking a bad fill. Actually, Bob is earning some money because Sui's price is rising. This is a random walk. I will mention it later again. So then Charlie is the interesting one here. This is the post-only off example. Charlie's inner spread is 50 basis points. That's wider than Alice, but it's close enough to the mid that as the price walks, Charlie's new refresh attempts keep crossing Alice's resting orders. With post-only off, those crossings aren't refused. Charlie just takes whatever fills results, so Charlie's chart fills in with fresh quotes every cycle. But his inventory keeps drifting as it eats from Alice's resting ladder. You are watching the cost of the I'll stay quoted no matter what choice. Charlie stays fresh, but it pays the spread to Alice every time it crosses. Okay, actually looks like everyone is profiting so far, but we'll see. I will now wait a couple minutes and stop the bots and we will see what each one actually traded. Okay, here's Alice. Look at the balances card. Alice started with 1000 Sui and 1500 USDC, but now you can see Alice net sold a big chunk of base into the market as a maker. That's from market activity buys that took Alice's ask, plus Charlie's refresh that crossed into Alice's resting orders. We can see them in here as well. Now, Bob is the clean contrast. Same Sui and USDC balances as it started with, zero fills, as you can see from here. Bob's white ladder, this one never got hit, which is exactly what we'd expect from this configuration. And then Charlie. You can see Charlie's net bought a big chunk of base as a taker, the mirror image of Alice's sell side. Charlie and Alice have basically been trading against each other through the demo, I mean, at least once. But yeah, there was a trade between them. Now, about the P&L. I want to be honest with you here. On a 3-minute demo with random walks, the P&L sign depends a lot on which way the price drifted between the trades happened and now. On this run, look at the totals. Charlie, whose net long base, ended up with the highest. Alice, who is net short base, ended up with the lowest. Bob is in the middle, exactly where it would be if it just held its starting position. On a different run with the price moving the other way, Alice and Charlie could swap places. That's just a directional noise. What's consistent across runs is the activity pattern. Alice and Charlie traded massively, Bob doesn't trade at all, and structurally, Alice is the maker capturing spread on every trade, and Charlie is a taker paying it. Over longer time horizons, maker age dominate the directional noise. In a 3-4 minute window though, the noise is what you are mostly seeing. So, 3 configurations of the same module, 3 completely different outcomes, and every bit of that came from the parameters we set at the executor creation time. Not from any bot side logic, not from anything off-chain. The configuration itself is a strategy, which you can just play with it. So, that's the Sui AMM, capability gated funds, a permissionless quote refresh, configuration constraints that the move type system enforces for you, and the hot potato refresh ticket that makes it impossible to leave a stale order on the book. The repository itself is meant to be a living reference, so fork it, run the bots yourself, race your own configurations against each other, and most importantly, have fun. The link is in the description. Thanks for watching.